hope everyone here can listen to me. And I just started the recording as well. So, so this is the third time we run the journal club. The first time we just cover Nelson and Trunks on linear algebra. So, now I will go slightly slower into the quantum information part. Uh, Today I'm supposed to cover the postulates of quantum mechanics, but I think I want to focus more on the first two postulates on the mathematics side of things. So without further ado, so I probably won't be able to cover block sphere, but some of the applications over here, when I discuss about block sphere, I will use it as well. So which is why I think the calculations are quite important for you guys to understand first. The first postulate, as we know, basically, if you have some isolated physical system, uh, when we want to describe it in quantum mechanics, we always use a complex vector space with inner product. Um, you don't necessarily need to use vector space. You just need the inner product structure. So if any state space with the inner product structure, we usually call it as a Hilbert space. Um, Even though we say that the system is completely described by the state vectors, so even though we say that the system is completely described by the state vectors, which is a unit vector in the system state space, uh, there is something actually redundant over here. This will be covered later on when we talk about global phases. So just to briefly talk about what does it mean. So let's say you have a vector with xi and yj. So let's say this is two-dimensional vectors, and let's say x squared plus y squared equals to 1. So this is sort of like a unit vector. Um, so the thing is, when you specify it as a unit vector, so whenever you multiply it with some, okay, I might need to write this vector in a complex setting, because in real setting you might not be able to see it. Yep. So basically what I mean here is that your vector v is a complex vector. So it means that your x and y will be a complex number. So you can essentially factor out a complex phase out of this vector, and they still looks the same, because what you are doing is actually, this is basically a unit vector, and you know that the amplitude of ei theta is equals to 1. So essentially you can factor out a global phase and the vector still looks the same. So in that case, the real state space that we should identify is not a vector space, but it's actually what we call as the space of rays, whereby you just identify the direction rather than identify the whole vectors. So we will cover this more later when we talk about phases. But right now, just understand that for Hilbert space, you can describe it. You can describe quantum states as state vectors inside a Hilbert space. Usually, we denote it as c to the power of n. So this would be the n-dimensional complex vector space. So the most important part is just the inner product. So that's the first postulate of quantum mechanics. The second one is on the evolution of a closed quantum system. It is usually described by the unitary transformation. So if let's say you have the quantum state of a system, let's say psi, at particular time t1, I will write it as psi, and then at t2 it will be psi prime. So how this is going to be related is through a unitary matrix. So this probably is not covered in undergraduate quantum mechanics if you study from the Schrodinger equation perspective. So equation 1 is actually just the same as equation 2, except that equation 2 you use the wave mechanics, but equation 1 you use the matrix formalisms. So they imply the same thing. So of course you can sort of like solve this particular um, differential equation to get this solution, equation 3, which basically means that your unitary matrix is given in this form. So over here, hash bar is an operator, what we call as the Hamiltonian. And it encodes all the information about the dynamics of your quantum systems, and it gives you the eigenvalues of the total energy of the quantum systems. So this is the part where I want to explore a little bit further. There are two questions that I pose over here that maybe you guys can try to solve. This is important later on for you to understand why in quantum mechanics we use Hermitian matrix and unitary matrix for different reasons. So let's look at the first question first. So if let's say A and B are commuting Hermitian operators, so A is Hermitian. If you forget, the meaning of Hermitian is basically this. When you perform conjugate transpose and it goes back to the original matrix, then it is called a Hermitian operator. Commuting means that when you perform the commutator, it is 0. So you need to use these two property commuting. They are commuting to each other, and then they are also Hermitian operators to show that e to the power of a multiplied with e to the power of b equals to e to the power of a plus b. I already sort of like hint at you that you don't need to do a large n, just do until n equals to 3. You need to expand the left hand side and the right hand side. And the way for you to perform a matrix exponential is by using this equation. This should be a, not x. So maybe I give you 5 minutes to work the first question out. If you are done with the first question, you can proceed to the second one if you want to do it first. So I'm not going to go through the very rigorous proof because we are not doing a mathematical course. But instead, we will just try to convince yourself that the left hand side is not equal to the right hand side unless they are commuting operators. So um, let's begin. So according to this equation 4, e to the power of a is the identity plus with a and then a squared over 2 factorial a cube 3 factorial. So you just need to expand until n equals to 3. So let's stop it here. So let's expand e to the power of b. So same thing. So that will be eb. So this is left hand side. So now let's look at the right hand side. I will let e to the power of z equals to e to the power of a plus b. So z equals to a plus b. So that I can simply write down the expansion. Of course, you can also write down without any trouble. So now let's do the multiplication on the left hand side. EA multiply with EB. It will give you something like this. So when you multiply them together, you get identity plus b squared over 2 factorial I think for this particular calculation, I just need the total power to be 3. So I don't need to multiply the rest, but instead I can move on to this. The reason why is because when you look at the right hand side, the highest power is to the power of 3. So I can ignore the power of 4 and above with my expansion on down there. So now you can collect all the terms. You get this. Let's put this here for now. Yep. You can of course write down like the b cube and then ab square, ab. You don't need ab cube, a square b and a cube and so on. I don't have space, so I just write up to square terms. So you can see that the first n, when n equals to 0, is the same. When n equals to 1, there's no problem. When n equals to 2, so you see that when n equals to 2, you get 1 over 2 factorial, 2ab plus a squared plus b squared. So remember that your ab does not have 2 factorial. So when I factor out the 1 over 2 factorial, I need to multiply by 2 inside. So this seems to be the binomial expansion of this term, right? But when you expand this correctly, so you get a square ab, ba, and then b squared. So you cannot group this term together because a and b right now they are not commuting. You can only group them together if they are commuting Hermitian operators. So that's why here is the part where you need to use the commutator. So if they commute to each other, then yes, you can write a squared plus 2ab plus b squared, and then your e to the power of a plus b will be exactly equal to e to the power of a multiplied with e to the power of b. If they are not commute, up to this point they are the same, but afterwards they won't be the same. So this is why only for commuting Hermitian operators that you can use this identity. If they don't commute, then whatever you are, if you use this identity, you are only approximating, you are not writing the exact solution. So let's look at the second question. Show that e to the power of ik is unitary for some Hermitian matrix k. You only need to expand until n equals to 6. So I will erase this part. And then perform the expansion again. So over here, you need to show that this is unitary. If you already forget what unitary means, it means that a matrix multiplied with the dagger equals to identity. So what you are going to do is that you let u equals to e to the power of ik, and then you define what is u dagger. So u dagger is conjugate transpose. So what you need to do is to apply dagger on everything. So you get e to the power of minus I k dagger. But k itself is Hermitian, so it's also equivalent to minus ik. So now what you need to do is to um, actually multiply these two together and at least show that until n equals to 6, you get identity. All right. So e to the power of ik, you would get identity, and then k. Sorry, you have I. I think this is minus as well. And then plus. Let's do it until here. I don't think you need until n equals to 6. That should be correct. So now you multiply these two together. Um, um, I'm too lazy to write down everything. But by right, you should be able to cancel off these two terms. And then identify ways to cancel off the k squared term. So k squared term, you have 1 here, but you have half here, but you have 1 here. So the other half is when this term multiplied with your identity. So you have minus k squared over 2 factorial again. So these three k2 k squared term cancel off each other. And then you identify like your k cube terms and see how they cancel off each other. Eventually, you should be able to get just identity based on your expansion until n to the power of 6. N equals to 6, sorry. This is not the perfect proof, but just to convince you that in order for some matrix to be unitary after the exponential, it needs to be a Hermitian matrix. So, which is why when you look back at your solution number 3, your Hamiltonian has to be Hermitian. so that the whole exponential term over here, they generate a unitary transformation. So that's the idea of this particular exercise. So let's quickly go to postulate 3. I'm afraid we don't have much time left. The third postulate is to describe what is quantum measurements. Basically, they are defined by the measurement operators, and these measurement operators, they act on your state space to give you some certain outcomes after you perform the measurements. This has to be Hermitian operator. The reasons being your Hermitian operators will give you the real eigenvalues, and those are the numbers that you can measure. So if you are given the state space to be signed, then the probability of getting a certain outcome would be given by equation 5. And the states immediately after the measurement, it will collapse into the eigenstates of your whatever measurement that you try to perform. So this will be the states after your measurements. We do need to take note that your measurement operators satisfy the completeness relations, meaning that when you sum out all the possible measurements, that gives you certain eigenvalues m, for example, that should give you identity. So in quantum information, we basically just focuses on projective measurement. And here I define very specifically what would be the projective measurement that would be interest to us. So it will be basically just the outer product of some eigenstates for the measurement that you try to perform that will gives you the eigenvalues m. This will be what we call as the projector, and they satisfy these relationships. Uh, it's not that difficult to see because I think this should be m prime. Yep, I think there's a typo. So it's not that difficult to see because for Pm prime dagger, so this is equivalent to m prime, and then you perform the dagger operation. It gives you back m prime, m prime. So what does it mean is that you have m of outer product, and then you have m prime. Yeah. So this gives you the chronicle delta, and then you need them to be on the same index, which is why you write here in the end. That's why you get this part on the right hand side. So then our expected value for whatever measurement m that we try to perform over here, it will be just your measurement outcome multiplied with the probability. And previously we defined the probability to be equals to equation 5. So in this case, because of this particular relationship, we can basically just write the projectors into the middle. And we can sort of like move the summation to be inside of this whole thing. So this is the whole summation. So initially this is PM. And in the end, this will be just the measurement that you are trying to perform. And this measurement takes a very specific form because we are taking the projective measurement. So this is what we will define the expected value of a particular measurement to be equation 9. I'm not sure whether you guys did this before. If you are given the variance to be this, so do you know how to transform equation 10 into this form? Maybe another 5 minutes to do it. So this is actually not as difficult as you think it is. The variance of particular observations is given by the expected value for this. So this is basically the definition. So what you need to do is to square the whole thing first. So you have m squared minus 2m, the expected value of m. So why do I not need to care about the multiplication between m and the expected value of m? Because this is a value and this is a matrix or operator. So when you multiply a value to an operator, it doesn't matter if you switch around the order. And then you have plus the expected value holding squared. So when you are finding the expected value for each of these individual term, you can actually break it down into the expected value of the individual term. So you have something like this. So because this is a value, 2 is also a value, so you can pull it out and you get the expected value of m. And then the expected value of m squared is also a value. So the expected value of 1 is just 1, so you don't need to write it down. So then you have something like this. And you get this. If you fail to identify what this is basically your variance equals to I think something like sum of x squared and then divided by n, something like that, minus something like this. So check back your statistics. This is basically statistics. So why this is important? Because this particular equation and combining with all the discussion about the Hermitian and commuting operators allow us to derive the Heisenberg uncertainty principle. So let's look at this question first. If you have A, B to be the Hermitian operators, and this is given by a complex number x plus iy. So I want you to show this. Maybe another 5 minutes. So just now I covered that this is the commutator. The curly bracket is the anti-commutator. So you only have AB. So now you need to find ways for you to generate BA. And you know from the properties of transpose or the dagger, if you have AB, dagger, or transpose, you get B dagger, A dagger. So because A and B are Hermitian, so they are the same. So that's how you generate BA. So what you need to do is to apply this. So then you get something like this. And you know that this is equal to BA. And so now this equals to x plus iy. So it becomes x minus iy. So then if you want to find the first term, then what you need is so I will directly just write AB minus BA. It will be x plus iy minus x minus iy. So you get 2iy. If you want to find the anti-commutator, so then this will be x plus iy plus x minus iy. So you get 2x. So that's how you get these two terms. So now the above implies that when your commutator term plus with the anti-commutator term, it will be the 4 times of AB. So you can verify this by plugging in all the term 2x, 2iy, and then x plus iy into the left side and the right side to verify that equation 11 is true. But now what interests us is to derive the Heisenberg uncertainty principle. So you need to apply the Cauchy-Schwarz inequality on this part. So Cauchy-Schwarz inequality basically means that if you have two vectors multiplied together like this, you can separate out into A squared term and the B squared term. And these two terms multiplied together must be bigger or equals to the one on the left hand side. So this is basically your Cauchy-Schwarz inequality. So now what you need to do is to plug this back to equation 11. So this is the first term, and then this is the second term. Uh, so this is the right hand side. And you know that this is smaller or equals to 4 times this. So then you can sort of like ignore this term because this is a positive term. So if you delete it, if it is equal to 0, then you get the equality. If it is something bigger than 0, then you get the lesser or equals to term. So this is what they did in Nelson and Chuang. So basically you ignore the anti-commutator term to get equation 13. Then the final transformation is to let C and D to be two observables in such a way that your A and C are defined this way, your B and D are defined this way. So this is the final step for you to obtain your Heisenberg uncertainty principle typo here. So later I will fix the typo. I'm afraid I don't have much time left, so I will just uh, show you what it is. So for this part, is basically sorry, this, and if you plug in the equation just now, plug into here, you get the expected value of C minus the expected value of C, the whole thing squared. And this is the identity that we tried to prove just now, equation 10. So you should be able to do it for A and B in such a way that eventually you get something like 4 the variance of C multiplied with the variance of D. So that is over here. On the right, essentially what you need to do is to change your AB into CD. So this change is not that difficult because what you need is to expand it. So you have this multiplied with this minus the D multiplied with the C. So if you do that, you find that eventually this is equivalent to the commutator of CD, which is why over here you change to CD. So that's basically how you would derive the Heisenberg uncertainty principle just by postulate 3 alone. I think I will just stop it for now. If you have any question, you can ask in the chat.